Yeah, so I was hoping to talk today about forward modeling interferometric observations of the epoch of reionization. So that's what I'll be doing. I'm not sure how familiar many people here are with this, this work. So I'll be giving an introduction first to what is the epoch of reionization, the EOR. Some of you may know it as cosmic dawn, sort of sometimes use those interchangeably, and 21 centimeter cosmology in general. I'll talk about some of the challenges that we face in doing this and so the current status of observations. And then I'll go into what I sort of really want to talk about and what I am most interested in, which is the role of a simulation in all of this, and particularly simulations for validating our analysis pipelines, but also simulations for doing inference to understand the physical parameters of the epoch of reionization. So after introducing the framework for that, I'll talk about simulating various components of the 21 centimeter universe, including the cosmology / astrophysics, and then the foregrounds, and then mock observing these with our instruments, our interferometers. And then if there's time at the end, I'll project and see what the future holds. I should probably turn this on. Okay, so first of all, what is the epoch of reionization? So to situate ourselves in the timeline of the universe, of course, the universe starts with the Big Bang. And then after that, we have dark matter and neutral hydrogen sitting everywhere, doing not much of anything. It's kind of, this homogeneous distribution across the universe. And there's no stars or anything like that. But of course, we've got structure formation because of the, universal expansion and gravitational collapse. The dark matter collapses eventually into dark matter halos, and eventually the size of these dark matter halos is large enough that the neutral hydrogen gas that's sort of tracing the dark matter is able to collapse into stars and galaxies. So when this happens, we kind of call that cosmic dawn, right? The universe is the lights are turning on, and you can see that here at about something like 400 million years after the Big Bang, and that starts our journey in this talk. That's where we come in. So the stars there radiating, they're changing the thermal properties of the IGM, the intergalactic medium around them. And eventually that first generation of stars will die, and the stellar remnants, the neutron stars, the black holes, are going to start emitting with X-rays. They're going to have a different effect on the IGM around them. And eventually you're going to get galaxies that are emitting UV radiation, which is going to ionize the neutral hydrogen. So you start off with almost completely neutral hydrogen. You get these galaxies that are ionizing the hydrogen around them in these sort of percolating bubbles. Eventually those bubbles kind of expand and merge, and you get the whole universe that is ionized. And so this process is called, obviously, the epoch of reionization. We expect it to last from about 400 million years after the Big Bang to about 1 billion years. So a greater part of the first billion years of the universe is traced by this process. Now, this neutral hydrogen that's kind of ubiquitous everywhere around this time, certainly towards the start of this the process, has a spectral line at 21 centimeters of wavelength, so 1.4 gigahertz in the spectrum. So this is observable with low frequency radio telescopes. And in fact, that's obviously redshifted by the time it gets to our telescope. So that's placing it at about between 400 million and 1 billion years after the Big Bang. It's a redshift of 30 to about 6. And so it's going to be redshifted down to to frequencies of about 50 to 250 megahertz. Obviously, the timing of all this is up for grabs because we haven't actually properly observed it yet. So that's what we're going after. We're building these radio telescopes to go and see this neutral hydrogen emit at the 21 centimeters at early. In the early universe, there's going to be a bunch of neutral hydrogen that's all going to get sort of ionized away. And at the end, we should have essentially no signal from neutral hydrogen at the 21 centimeter wavelengths because it's all been ionized. And so the physics of star and galaxy formation and a bunch of other stuff is all encoded in the brightness temperature of this 21 centimeter line. So the goal of 21 centimeter cosmology as a field is to extract cosmology and astrophysics of the early universe. By early universe, I'm talking redshifts greater than 6 from observations of the redshifted 21 centimeter line. So, why is this cool? Why are we doing this? And the reason is that this is just it's sensitive to a lot of different processes, right? So this brightness temperature that I mentioned is the flux, the brightness of this emission of this particular spectral line. And it depends on a number of physical processes. It depends on the matter density. So it gives us sensitivity to dark matter and structure formation and the overall structure of the universe. It's also dependent and sensitive to the thermal state of the IGM, which depends on stellar properties. So the first generation of stars, black holes, and galaxies affect the thermal state through this parameter TS here. It also depends on the background radiation, which ostensibly is the cosmic microwave background, but could also include other sources. And it also very clearly depends on the ionization state, right? So as the neutral hydrogen is ionized, it no longer emits in 21 centimeters, and it's linearly proportional to the fraction of hydrogen that's ionized. Right, so yeah, so the brightness temperature is a spatially dependent quantity, and it depends on all these things, which are all spatially dependent quantities themselves. And so because we're sensitive to all these things, we can infer by measuring this quantity, we can infer things about structure formation, dark matter properties, and dark energy, things like that. But also even more clearly, we're going to be sensitive to properties of the first stars and galaxies. And so there's lots of useful quantities and properties that we can get from observations in this epoch that we can't really get any other way. The other really cool thing about this, about 21 centimeter cosmology, especially, I mean, at all redshifts, but especially at high redshifts, is that we have so many modes available to us. We have such a large fraction of the volume of the observable universe available to us, much more than the cosmic microwave background or the low redshift galaxy surveys, which enables new parameter spaces, I guess, of science to be inferred. So this is why over the last decade or so, many low-frequency radio telescopes have been built to observe this, primarily to observe the epoch of reionization. We have the MWA, Murchison Wide Field Array in Australia. We have LOFAR in Europe. We have HERA, which is the US-led telescope, but it's situated in South Africa, and that's what I'll be talking about. That's the experiment that I'm primarily a part of, and then a bunch of other smaller experiments as well that have done a lot of good work in this area. So how exactly do these telescopes work, right? So we actually have two kinds of telescopes. As I said, these are tuned between the frequencies of 50 to 250 megahertz to trace that evolution of the EOR over its history between something like 400 million to 1 billion years after the Big Bang. We have interferometers, which are the bigger and more complex of the two kinds of experiments. These are multiple antennas correlated between different baselines. So each pair of antennas constitutes a baseline, which observes a particular angular scale on the sky, a particular Fourier angular scale on the sky. Then it observes obviously different frequencies, which builds up a full 3D picture of the universe. These are extremely computationally intensive. They take a lot of data, multiple terabytes of data. In fact, the SK, I think, will be taking multiple terabytes of data per day when it comes online eventually. So on the other hand, we have global experiments. These are typically a single antenna. You can see the one here is edges. Oh, I should mention the one on the left here is a rendering of the HERA experiment, which is, again, what I'll be talking mostly about today. It's a close packed hexagonal array. On the right, you see the edges antenna. which is an experiment I'm also a part of. This is a single antenna that's taking, an average temperature, brightness temperature of the sky at each frequency. So it's measuring the thermal history of the universe as it evolves through this epoch. Right. So what are the challenges that we face? Well, the one that always comes up when you talk about 21 centimeter cosmology, and this is true for high redshift, epoch of reionization stuff, but also lower redshift stuff, that's done by experiments like CHIME, for example, is the foregrounds. The foregrounds, we have our own galaxy is in between us and the thing that we're trying to see. Our galaxy emits at these frequencies between 50 to 250 megahertz. It's obviously not 21 centimeter radiation, it's synchrotron and free emission. It's about 100,000 times brighter than the signal that we're trying to look at. So it's really a big obscurant. However, in principle, it's easy to separate these foregrounds from our signal because the foregrounds are extremely smooth in frequency, right? They're essentially a power law in frequency. So they're really smooth, whereas the cosmic signal is really structured. The cosmic signal traces, each frequency traces a redshift, and so you're looking back at different parts of the universe. So you're going to have, either a lot of neutral hydrogen or not a lot, depending on where you are in the universe. So it's up and down. So because of that difference, you can, in principle, easily separate these. But this is complicated by the instruments themselves, which impose, different structures on the signals that we receive. And if any of those, those systematics that get imposed on the structure, on the signal, are spectrally structured, that leaks those foregrounds back into the space where we would hope to see the cosmic signal, right? And this is particularly bad because the foregrounds are so bright. We need to have systematics that are smooth in spectral space to about 10 parts per million, right? This is kind of unprecedented accuracy for these kinds of experiments. And this hasn't been achieved yet by any experiment. So this is the big challenge, to get these systematics way down, really smooth. It's not that there has to be no systematics. It has to be that we know our systematics, and they have to be spectrally smooth. All right, so that's the main challenges. There are other ones as well, but that's the main ones that are kind of come up in this talk. So throughout the talk, I'm going to talk a lot about the power spectrum. This is the main kind of metric that's used by all current interferometric experiments. So most of you will be familiar with the concept of the spatial power spectrum, either with low redshift galaxy surveys or otherwise. But this is the main metric. So the power spectrum is just a measure of the spatial variation in at different scales, right? We average it in 3D shells, so we get a 1D power spectrum, assuming isotropy and homogeneity in the universe. But small k here represents large scales, and large k represents small scales. And the power, the higher the power, the more fluctuations there are. So the relevant things here, so the colored lines are supposed to represent the cosmic signal here, and we take power spectra at different redshifts, right? So at each redshift, we take a little chunk and say this is approximately a homogeneous part of the universe. It's they're all close to each other, so it's approximately homogeneous. We take the power spectrum there, and then we go to the next redshift and do the same thing. So you get this evolving power spectrum as a function of redshift. Its general characteristics are that on the large scales, there's more power than on the small scales, but it has a reasonably significant power on the small scales as well. The foregrounds, on the other hand, because they're very smooth, their Fourier transform, which is very closely related to the power spectrum, has a lot of amplitude on the large scales, and then dies off very quickly as you go up to smaller scales. And so it dies off much more rapidly than the epoch of reionization or the cosmic signal. And so you expect that the cosmic signal will kind of poke its head out at these larger k. However, you've got this competing effect where you've got thermal noise, right? So thermal noise from the instrument, just random fluctuations, is essentially white noise, and so it's flat in K, and that level will go up and down depending on how many antennas you've got, how large they are, how long you're looking at the same place in the sky, etc., etc. And so you can bring that down. What you want to do is bring that noise down enough so that your signal can sort of poke its head out here, and you have this window of looking at the actual cosmic signal. There is a problem, of course, with anytime you want to bring the thermal noise down, you need to have more antennas or be looking at the same place for longer, and that means you need a lot of stability, which increases the risk of systematics. And so, in terms of what I was saying just before, in terms of systematics, the foregrounds ideally look like this. If you're going to have a systematic which is spectrally structured, it's going to basically bring the foregrounds out like this, and it's just going to completely cover the signal. All right, so that's the power spectrum. So what's the current status? What do we know about the EOR so far? Well, before 21 centimeter experiments really got going properly, we did know some things about the EOR. We kind of knew that it had pretty much fully occurred by a redshift of about 6 through other observations of Lyman alpha, high redshift quasars, UV luminosity functions in the CMB. We had some handle on this, but not anything very specific, right? We can say that it ends at around that redshift 6, but we don't know how it progresses during its evolution. The first observation of the actual 21 centimeter signal was presented in Bowman et al. 2018. This is by the EDGES experiment that I met and showed the picture of that antenna before. So this was a pretty widely known result. It caused a bit of a stir in the community 4 years ago now. So this presented the first evidence of the earlier star formation at about a redshift of 20. And so you can see the observations here, multiple different cuts of the data that you can see. But the universe is evolving from left to right here. So you've got this flat. Remember that what EDGES sees is the overall emission or absorption of the 21 centimeter radiation with respect to the cosmic background. And so, before the stars form, it's essentially 0. It's just following the cosmic microwave background temperature. Then stars form and causes Lyman alpha coupling, and it cools with respect to the background. It would keep on going down, except that at some point those stars die. They get recycled into stellar remnants, black holes, neutron stars. They emit X-rays and start heating up the gas around them, so that it sort of has this turnaround and goes up. And then at some point, the UV radiation starts to ionize things. And of course, if all of the hydrogen is ionized, you get no signal at all, so it would go back to 0. So that's very much the general expected shape that we would expect to see, which is nice. However, it has a lot of surprises in it. So here you can see the EOS simulation of, it's kind of a typical simulation of what we expect in this era. And you can see that the amplitude here is much, much lower than what we observed. In fact, the amplitude of what was observed is so large that standard astrophysical scenarios just cannot reproduce this. So people were suggesting that there's a different dark matter candidates that they could exotic dark matter candidates that could produce this effect, or other sources of background and things like that. But there's always the off chance that this is just a systematic as well. So just very recently, CERES-3, which is another global experiment, put out their results and showed that within their noise levels, they don't see any absorption feature, and it's sort of very discrepant with the EDGES results. So the jury's still out on how much of this is to do with systematics. It's a very difficult question. People like myself are working very hard on trying to answer it, but we'll see what happens in the future. Okay, what about interferometers? Now, as I said, interferometers, they measure the power spectrum. That's what we're all going after. In principle, they can measure the full 3D universe, but at the moment, we average it down to a power spectrum to beat down the thermal noise. So recently, at the end of last year, the HERA collaboration published the most stringent upper limits on the power spectrum to date, so at redshift of 8. You can see that this upper limit now, and I say it's an upper limit is because there's thermal noise. So basically we know it's the real signal's below our thermal noise level somewhere, but we don't know where it is. So we've just placed an upper limit. There's also almost certainly some systematics that are in there as well that are also below the thermal noise level that we haven't come across yet. But in any case, it's the lowest thermal noise that we can be sure of so far in the field. It's still about 2 orders of magnitude above the some theoreticals, the fiducial theoretical signals that we might expect. So we still have a little ways to go. But this doesn't stop us from doing some interpretation. So we also had an interpretation paper where we used multiple different models to try to see what this would mean. And the basic outcome is that there is a class of models of reionization that are ruled out, and that class is what we call cold reionization. And that's the case where you start reionizing. So you start with your UV radiation before you ever really heat up the IgM with X-rays, right? So somehow you don't have those stellar remnants heating up the IgM before you start ionizing. That's essentially ruled out quite strongly by the data at this point. So the overall status of the field is that we've been focusing on these upper limits so far, where it's pretty easy to, well, I should say easy. It's very hard, but in some ways it's easy to place an upper limit because you can say I've got systematics, I've got thermal noise, they're all below this level, and that's what I'm going to call it. But to go from an upper limit to a detection takes a lot of work, right? Because you've got to now say, not that there are some systematics, but they're below my thermal noise. You've got to say, I understand how those systematics, what level of systematics are still there and how they affect the uncertainty in my estimate of the actual power spectrum. And then to go the further step of a detection of the power spectrum to doing inference on that power spectrum with cosmological models and astrophysical models is another level of having to understand what your systematics are really doing and their correlation with the parameters of the astrophysics, et cetera, et cetera. So that's what I want to talk about today. Is how do we go from one to the next, and that really involves precision simulations. So I want to talk about forward modeling, which what is being done in the field at the moment, and traditionally, for the last 10 years or so, is we take data that's got all sorts of rubbish in it, and then we come up with algorithms that are supposed to remove the rubbish, right? We try to remove the foregrounds, we try to remove cable reflections, we try to remove crosstalk, et cetera, down to get a power spectrum where we think it's as clean as it can be, and then we would try to compare that power spectrum to some simulated power spectrum that we get from some kind of astrophysical simulator. This is fine. This is what was done for the interpretation that I just showed on the previous slide for HERA. This is fine, but of course, at some level, you're never taking out all of the systematics, right? You've got some level of residuals in there, and you need to understand the posteriors of those residuals given the priors you have on your systematics to be able to understand the posteriors on your astrophysics. And that's something that we don't have a good handle on yet. And so forward modeling would go the other way, right? So we take our cosmological and astrophysical signal, and then we add to it the foregrounds, and then we mock observe that with a telescope, and then we add various systematics of the signal chain onto that, and then we end up with a product that looks just like our data, hopefully, and then we process that through the same kind of processing pipeline as the data to get all the way through to being able to compare it to what we knew the input was, right? And at this point, we can do one of two things. The first thing is, if we've done that really well, we can compare it to the input and say, okay, I know what I put in, I know what I've got out. Do I have a bias, right? I put in a power spectrum of this, and I've got out a power spectrum of this. I know there's a bias. Therefore, something in my correction, correcting the data or reducing the data has gone wrong. So this is a way to validate the analysis pipeline, right? If you've created the data in the exact same format, the mock data in the exact same format as your real data, this is a really good test of your pipeline accuracy. Of course, what you might want to do after that is to do actual inference, and that requires you to run this sort of tens of thousands of times, right? So you input, you change the physical parameters, or you change the foreground parameters, and you run multiple realizations in some kind of Monte Carlo simulation, and you can marginalize over the nuisance parameters and get to robust posteriors on your physical parameters. That would be the ultimate goal. So we'll talk about that a little bit, but that's kind of very much future looking. Okay, so this will be quick because I've already kind of explained this, but looking a bit more closely into interferometers, so far we've had success in producing a cosmic signal, and then directly from that going to a power spectrum, and then comparing that to data where we've tried to remove everything, right? And then we can either do inference or validation. But what we want to put in is these extra steps. What we want to simulate the foregrounds, and there's multiple foregrounds, right? There's point sources, there's other galaxies, there's our own galaxy, there's extended sources, which are kind of close by galaxies that are large. We also want to mock observe these with our telescope, and then we want to add systematics, and there's various systematics. So through the talk, I'll be talking about kind of each one of these components individually and the work that we've done so far on them. Doing inference with all of this, as I said, is a little bit pie in the sky. It's a little bit, of a dream. But we have already written some, prototype frameworks to do this. So my student Bella Nazarudin published this paper a couple of years ago, where she actually, on top of 21CMMC, which is like the de facto standard code for doing this kind of inference, as I showed, was used for HERA in the interpretation I showed before. On top of this code, she built a framework where we can take, the cosmic signal, but then we can, put in a component of foregrounds, and we can put in a component of mock observing and systematics, etc. And you can put in and take out all these components as you like. So that's the whole framework, right? So she basically established a whole framework. There was a couple of downsides to that work, or limitations to that work. One was that each of those extra components usually take a long time to run, right? They're very computationally intensive. So we used approximations for some of those, and those approximations led to the kind of poor posteriors that you can see for some of these parameters. So they can be cleaned up if we do better in terms of those approximations, but that's hard because it becomes unfeasible if you're doing it exactly. So thinking about how to speed them up is one useful thing. Secondly, also because of the speed here, while the components were in place to do each of these, we didn't actually vary the parameters of each of those other components. We still only varied the parameters of the astrophysics. And the reason for this is that the systematics in these other components is extremely high dimensional. We're still unsure of the best representation, but the best basis set essentially to represent those systematics in. So we're still, needing to work on that by actually going to data and doing some modeling. Okay, so what has been the progress in simulating the 21 centimeter universe? So the first thing to simulate is the cosmic signal, and if you think about the program that we've set up in terms of having to do the cosmic signal, add the foregrounds, do the mock observing, you need a cosmic signal that you're not just producing the power spectrum, right? You can't just go from parameters to power spectrum because you need to do these intermediate steps. So what we actually need is a 3D realization of the universe for each set of parameters that we use. And it needs to evolve over time. So that involves 3D light cones. But on the other hand, we need this to go really fast. So we can't just use, hydro sims. They take way too long. On the other hand, we can't just use like an emulator for the power spectrum because that misses out the crucial middle steps where we would add the systematics. What we at the moment are using, and has been quite successful, is a code called 21CM fast. It's a semi-numerical code. So it involves the density field, using Lagrangian perturbation theory, and so that's quite fast. And then it finds halos on this, and then it paints onto the halos the brightness temperature based on extended pressure formalism. which it's quite fast and it's been quite successful. It's shown to be about accurate to within about 20% with hydro sims, which is actually very good. I mean, 20% doesn't sound wonderful, but when you think about we're 2 orders of magnitude off the actual signal here in terms of observation, 20% is small chips. So yeah, that was published in 2011 by Andre Messinger, and I updated that code 2 years ago. It also, and very usefully, simulates alternate observables. So it doesn't just give you the brightness temperature field at the end. What you get out is a bunch of fields that the brightness temperature is dependent on, right? So if you go back to that equation that I showed at the start, the brightness temperature is dependent on a whole bunch of different processes. So you get the dark matter density out, you get various radiation fields out, you get importantly you get the ionization fraction here, the XH1, and then finally get the brightness temperature. So you're actually able to use these other alternate observables as consistently. So if you come up with a likelihood in the end of a power spectrum for 21 centimeter, you can also consistently use the XH1, the evolution of the neutral fraction, at the same time compared to another observable that you would get for that observable. So you can use 2 things at once. And this provides extra constraining power. So at the moment that's the best tool we have, and so hopefully we'll be improving on that in the years to come as well, making it a little bit faster and adding more realistic physics to that. So what about foregrounds? I'm actually going to skip through foregrounds a bit because while foregrounds are super important and that they're super bright and they're really extremely important for doing calibration in a lot of ways. As I said, because they're so smooth, we can kind of get around them. As long as we get their magnitude roughly correct and we get the brightest things in the right places. And as long as we're getting our systematics right, then the foregrounds don't matter quite so much. But the status here is typically within HERA, we would use the GSM, which was published in 2008, and then we'd use, which is a map of the diffuse structure from the galaxy, and then you would you'd use GLEAM to add point sources onto that as well. So GLEAM is a survey done of the southern sky with the MWA at these frequencies. So it's the biggest survey of this kind. So we would add those point sources in, which we treat as literally exactly point sources, and we might add some other fainter point sources via some statistical model. The problems that are here, polarization. No one's done a whole lot of work on making sure the polarization here is all correct. That could be a problem in the future. There are missing, times in GLEAM due to the galactic center. So, you have to try to fill that in, or you've got discontinuities, and discontinuities are the bane of our existence. So even discontinuities in time, because of the way that our instruments work, actually translate into discontinuities in frequency. And as soon as we get a discontinuity in frequency, we're stuffed because that's a spectral structure. And then there's this problem of extended sources. We don't have particularly good models of sources that are small but kind of blobby on the sky, and that can get a bit tricky. So we would love more accurate sky models, but once that's not our biggest bottleneck at the moment. Okay, what about simulating visibilities? This is a problem that takes a lot of work. Let me try to go through this. So this is the visibility equation. So what we actually observe for a particular pair of antennas sitting on the ground, we correlate their signal, right? And so what we observe, we call it visibility. The baseline here is just the displacement vector between the two antennas, and then we've got frequency. And what it's doing is taking an integral of the upper hemisphere of the sky. And so the effective sky is A is the sensitivity of the instrument to different parts of the sky. In general, it's a complex quantity, and then you've got the temperature of the sky at any particular location as well, right? So it's just the effective sky, the integral over the effective sky times this Fourier transform kind of fringe. There's a bit of a complication because it's not exactly a Fourier transform. You can't literally just do a fast Fourier transform here because, for one, you're only doing it over the upper hemisphere. So LM are these projected coordinates. They're like the sine theta kind of thing, so that you get out to 1 at the horizon. You're doing it on sort of like unit disk. And then you've got this spherical distortion, of course. So you get this spherical distortion term here and in the fringe. So you can't just take a fast Fourier transform to it in general. You could in previous, for previous telescopes that have that are very large and they're kind of looking right at zenith or whatever, and they have this very low sensitivity towards the horizon. You could kind of approximate their whole area as going to infinity, as going to a 0 and then just extending out to infinity. We can't do that because our beams have significant sensitivity at the horizon, and so all of these effects have to be taken into account. So when you think about this for HERA in the future, we're going to be doing something like 10,000 baselines, right? And 10,000 times per day, and 1,000 frequencies. So that's like 100 million. Am I right there? Yeah. No, 100 billion. Sorry, 100 billion Fourier transforms per day, which is obviously a computational challenge. There are lots of ways to approximate this, essentially. There are ways to represent the discretization, because anytime you take an integral over a diffuse field, you have to discretize the integral some way. And so there's different ways you can discretize that. Some are in image space, some are in like spherical harmonics, but in either case, you have to discretize it some way. You can use the flat sky approximation, which means you can do a fast Fourier transform. It's an approximation, doesn't work that well in our cases. And so the point is here, there are multiple ways to do this, which has resulted in a number of simulators that do this. Some examples are the CASA tool. There's Prism, Hilbers, Rhymesy. There's a bunch of every man and his dog has their own homebrewed visibility simulator as well. So there has been this effort, and mostly led by the HERA project, but it's kind of separate from HERA itself, to come up with a simulator that makes no approximations. Right? It's extremely slow. They make it as fast as possible, but it makes no approximation. So it's kind of like a reference simulator, which is going to be useful for testing other simulators against. It's not bad to make approximations. It's bad to not know what your approximations are doing to your final power spectrum estimation, right? So PyUVSim is this effort and is a simulator. It also defines nicely, it defines a configuration for simulations. It sort of says, okay, I know everything I need to know to be able to do a simulation. It comes up with a configuration standard. And so we've got this other project, which I lead in HERASim, which uses that configuration standard to be able to wrap a number of simulators. So we've actually wrapped 3 or 4 simulators so far, where you can use the same configuration input and choose a different backend simulator to simulate the same thing, but with a different simulator, and go and compare them. So it's unified interface. So that's something that I've been involved with. Okay, I'm aware that I'm starting to run out of time, so I'll keep pushing through. So one big problem you have with simulators, again, is this accuracy. Especially if you've got a diffuse structure, right? It's just sort of this pattern on the sky. You've got to choose some way of discretizing this, and you've got to know what kind of errors you're inducing because of that discretization. So one way to check this is by coming up with analytic solutions, right? Coming up with test patterns on the sky that you can compute analytically the visibility for, and then comparing your simulator in these number of cases to make sure it's doing the right thing, and to understand the level of error. So in this recent paper by Adam Landman, myself, and Danny Jacobs, we actually produced a number of these solutions. It's not trivial to come up with these solutions. There's only a relatively few number of sky patterns that will afford computable solutions. But that's what we did. So all our solutions there. What we found, two kind of conclusions from that study. The big one here is that you can't treat the Fourier transform of a Gaussian as a Gaussian. right? So obviously on an infinite plane, if you have a Gaussian, you take the Fourier transform, it's a Gaussian. And people have used this to build sky models, right? They say, my sky model is a series of Gaussians, and I can Fourier transform that really easy because I just take the Fourier transform of each of the Gaussians and add them up. You can't quite do that because, again, the space we're on is not infinite, and so the Fourier transform of Gaussian on the sky is not quite a Gaussian. We found an analytic result which, to leading order is a Gaussian, and then you have extra terms that go out from there. And we found that you had to go at least to second or third order to get 1% accuracy, and we're looking for 0.01% accuracy in some of these simulations. But the analytic corrections are quite easy now that we've computed them. So this should be useful for simulators down the line. The second thing we found essentially is that wide skies, we took a particular pixelization of the sky and tested it just to show how it would be done. This pixelization is just a heel pixelization of the sky. And we showed that when you had wide patterns like a monopole, right, just a uniform sky from horizon to horizon, your visibility simulator does particularly poorly, right? So you can see up here that especially for where you didn't use many pixels, or the resolution's not great, you've got like 10 to the -3 accuracy, which is not good enough for our simulations. But as soon as you get smaller, more compact sources, you get very, very good agreement. Okay, going on to more HERA related things. So HERA Sim, the package I mentioned before that sort of wraps different simulators. Also, its main purpose is to be able to add systematics and essentially HERA specific systematics to our simulations. These are the limiting factor, right? So I said foregrounds are the big thing, but actually the systematics are the limiting factor because they're the things that take those foregrounds and spill them over our whole Fourier space. So this is able to add RFI, complex gains, crosstalk, cable reflections to our visibilities, our simulated visibilities. And so you can see a few of the examples of that here. I was going to go through and sort of explain each one of these here, but I won't do that for want of time. But you basically can see that you've got the EOR here. Foregrounds are super bright, but you could still go to out here and see the EOR, right? But as soon as you have cable reflections, for example, they take those foregrounds and spill them out here, which covers your EOR up. And so you get this total space here where the EOR is quite obscured, and we have to go then and remove these. Obviously, when we remove these, we run the risk of also removing the EOR signal, and that's what we're trying to validate, right? And so we had this big project with the data release that came out with the most stringent limits to date. We also did a big validation project to make sure that the analysis wasn't removing more signal, like removing EOR signal to a significant extent. So, so we actually created the most realistic simulations of full observed data ever, as far as we know. They were in the exact data format. So once we got the data products, they looked and felt just like the actual data, the full amount of times, the full amount of frequencies, the full amount of times frequencies and baselines, that's the other one. There's about 4 terabytes of mock data. What we didn't do was add RFI residuals, antenna position errors, or polarization. So there are 3 things we didn't do. However, we did for the RFI, while we didn't add RFI residuals, we did flag the same RFI patterns as were in the data, because that can cause issues as well. And so we did this with a unique validation approach. All of the tests that we did, so we did a bunch of small scale tests on different components, individual tests, and we wrote each one of those up as a Jupyter notebook, which is publicly available on our repository. Each one of them was sort of peer reviewed within our group to make sure that we were doing the right thing, and it has a specific format where we checked off that it met criteria. Excuse me. And so that was kind of a unique validation approach until we got to the full end-to-end run. And so that full end-to-end run, here's kind of the money plot from there. This is the input power spectrum in gray. The blue is the power spectrum of the full data. And so you can see at the small k, it goes way up because of the foregrounds, which is what we expect. Up here, it's kind of flat because of the noise. The blue has the systematics in it, and we never took them out, right? So you get these this bump here, for example, where we know that that's just systematics, and what we recover after we remove the systematics in orange is actually consistent with the input power spectrum. In the process, we did actually uncover 3 sources of scale-independent bias, so where the whole power spectrum goes up and down because of various biases, and we were able to correct for these. And these were, specifically found by doing this validation process. All right, so I'm kind of at my time. I can kind of skip through some of these, and if people have questions, we can talk about them. But in terms of the future, the next HERA data release and the next are already on the cards. We already have the data in the can, which is working on them. The very next HERA data release will be 10 times the data with these. So I should have mentioned, I somehow didn't mention this. The first HERA data release that has the most stringent limit so far was with 19 antennas. There will be 350. In fact, we've already built 350. We haven't connected them all yet, but it's a very limited subset of the data. So the thermal noise was quite high. The next data release will be with 10 times the data, the same number of antennas, but 10 times the number of nights observing. In terms of validation, this just means 10 times the amount of simulation, which is a bit of a project. We're using a faster simulator this time. It's a GPU simulator, but we're actually not using it in GPU mode yet for a couple of reasons. We're having to do some tricks to average the data prior to saving it to disk and make sure everything's okay there to actually be able to feasibly do this. The next will be a bigger project. That'll be many more antennas and these new feeds, which have lower systematics, which is awesome, but they're new systematics, which means we have to newly model them. It'll be even more data, so we'll need to get clever about how we do this. We'll probably have to use actually the GPU mode on our new simulator. And we'll be using a more realistic crosstalk model. So crosstalk is where you get radiation coming in, hitting this feed here, and then bouncing off and going into this feed, et cetera, and all the other feeds and all that. So that actually incorporates a lot of spectral structure, which we obviously don't want. So we need models of that spectral structure. So we have this new physical-based model of that by Alex Yasiadis. Okay. In terms of performance, I mentioned this GPU simulator. You can see how much performance gain it's giving on our initial tests, factors of, well, more than 10, maybe 100. Speed up by going to GPU, but it still needs to be, has a little bit of work to do to make it as general purpose as the other simulators, which we will require. In terms of modeling for inference, I've talked a lot about validation because the inference is too hard, but we have done some work here as well. So my student who published that framework, that prototypical framework that I mentioned at the start, has recently published a paper where we look at beam models. So the beam models are extremely highly dimensional and very complex. It's hard to know how to parameterize them. So what we did in this paper was we used a PCA basis to compress the information in the beams. We got the relevant information down to about 20 parameters, the eigenvectors of the PCA, and we can use those in an MCMC context to marginalize over them. And so by doing this, we reduced the errors in the power spectrum, the estimated power spectrum, by a factor of about 10. We could, that wasn't accounting for calibration. So, the biggest source of error from the beam comes from the calibration. So this would make a much bigger difference when we incorporate that as well. So we'll be building on that. Can we build such models for all systematics? Doing something like PCA? Probably not quite, but we're working on it. is the plan for the future. I'll just leave these up, I think, and people can ask questions if they would like. Thank you.
Great, thanks. I'm gonna do, I have some questions, but other people should go first.
Yeah, I was just gonna say thank you, students, for the workshop. Do you have any questions? No. I don't see any hands raised on Zoom, so
Yeah.
Go ahead and start with your question.
Yeah, good. So one was you had a fun lead off about 3 things that caused a scale independent bias, which you guys removed. What is there a short answer to what that was?
Yeah, you know what? I should have put a bonus slide in here for that, but I can't. Yeah, I can say. So the three things that you expect potentially to cause bias, and when I say bias, I mean signal loss. Right? We're talking about upper limits here. Anything that adds power is not going to bother us too much at the moment. Anything that removes EOR power is a problem. And so one of those areas is when you're averaging visibilities together, which you expect to be redundant or like identical. Yeah. To beat down the noise. If they are not identical, because they're complex numbers, they actually average towards zero. They decohere. And so that's one place you expect to get some, and we did find some. We found about 3% bias because of that. The other place you expect to get it is when you remove systematics, right? So if you go back to, if I go back to this plot kind of here, this is a oversimplification, but when you think about taking away these systematics, you're thinking of going, chopping this out and chopping all this out, and then trying to focus on areas where you've got the EOR. When you chop it out, you're going to chop out some EOR, so you expect some signal loss from that. We found that to be the case as well, but again, it was I think it was a 2% effect, and again it was scale dependent, which is nice, right? So it's not like we have to remove this kind of complicated bias. It was just a 2% everywhere thing. The other place we got a bias was in the absolute calibration, which I didn't really talk about here, but when you go and calibrate the gains, if you underestimate all the gains, then you add power. If you overestimate all the gains, you you remove power from the whole, from everything. And so we for a specific reason, when a bright source came up, I think it was Fornax A, when Fornax A comes up, it screws with the statistics of how you do absolute calibration. And we found that we had an overall 5% bias, which is actually fixable at the source code level, right? You can go back and fix it so that the statistics is right. We didn't in this iteration because we had, it had already gone through too far. It's also scale independent, so we just fixed the overall bias. But for the next data release, that problem will be fixed completely.
Yeah, and then was that due to compression or something else?
Compression,
like analog, like of the instrumentation itself, or was it just a?
In terms of the abscal bias, it was purely an analysis thing. Okay. Yeah.
So, yeah, just because we see we have a similar effect in Chime that is well, it's not analog bias compression, it's compression in our digital electronics, and so we have a subtle correction that we end up having to make for brighter sources that. Oh. Yeah. Anyway, that Juan wrote up in a paper a few years, probably 4 years ago at this point, but yeah.
Oh, that's interesting. Yeah, no, it's definitely not that source, although I can't speak for whether we've also dealt with that source of bias or not.
Yeah, and then I had one other question, which was like way back at the beginning, and you don't have to go back that far in the slides. You had basically your overall picture of how you do the, how you inject your systematics, and you injected them after the visibilities themselves.
Yeah.
Yeah, like that forward. Yeah, there. So you added the systematics after you put, after you formed the visibilities. I imagine that's more computationally feasible than trying to put it before. But yeah. Is that a yeah? Are there any systematics you try to inject directly, before you form the interferometric visibilities, or are all of them basically handleable after?
Yeah, so that's a really cool, good question. So, I mean, just thinking of the signal path, right? This just follows the path of the signal through the universe through our telescope, and then most of these systematics, well, the beam is not one of them. The beam actually really comes in here. Yeah, no, that's that's very true. That actually we do put here, so that's just a misrepresentation on my part. But certainly RFI is best modeled after the visibilities. Gains are best modeled after visibilities. Crosstalk. Well, so cable reflections are really happening in the cables after you've created the visibilities. But crosstalk is something where it really should be before the visibilities. But yeah, because this step is so computationally expensive, you want to do as much as you can after it, so you can swap that out easily without recomputing the visibilities. Yeah, so it is. Some of it is computational, and some of it is that's really where it is. The new crosstalk model that I mentioned is also post visibilities, but it kind of it requires you putting in all the visibilities and then cross multiplying them again in some way. So it's not necessarily that much cheaper than putting it in before the visibility simulation.
Yeah. And then what's the largest, is HERA the largest scale you've run this on so far?
Yes. Yes.
Yeah.
And in fact, yeah, like as I said, we're running this for HERA. I think I said 19. Now I'm struggling to remember if it was 19 or 30 antennas for some reason. I think it was 19. I'm pretty sure. Anyway, we ran it on this sort of initial subset of the antennas, and that's 4 terabytes. Of data. And so as we go forward, this next one that we're currently working on right now, the next data release is 10 times that data volume. But we're using sort of clever methods where we never write it to disk before we get to where we LST bin. So we kind of average it down before we ever write it to disk, which helps a bit. But yeah, going forward, it's going to be interesting. We're going to need faster solutions to be able to really do this.
Yeah, in Chime, where we have many more elements but fewer reflectors, we definitely have issues scaling up our simulations all the way to full Chime level. So I'm interested in various solutions you guys come up with too.
Yeah, and vice versa, of course. Yeah, the GPU, the GPU scaling seems to be somewhat incredible. And it depends. Our GPU simulator you have to take advantage of the GPU, right? So if you go to you're well aware of this equation, but this fringe here. So I've written the A here as the beam, but actually in real life this is the product of the beam of the 2 antennas, right? And you can take the square root of the sky, and then you can take this as a product of one of the antenna locations with in the fringe and the other antenna location in the fringe. And there you can make it essentially just one big matrix product. And then your GPU becomes extremely effective because it's just doing linear algebra at that point. And so we found that to be a huge speed up, but then you've got the other problems associated with going to GPU. So.
And then where do you run, are you just running this on a local cluster at ASU or Berkeley or something, or do you go to a full?
Yeah, we've got a few places. So we've done some of this on the what's it called? Through XEED resources. But we've also got a supercomputer in South Africa where we have a fair bit of time. So we've got up to 800 or 1,000 cores. Something like that there, where we can do some experiments. We also use NRAO resources. So yeah, we spread it out. So I should say this inference, let's go back, sorry. This inference here, it took about a month to run that particular inference. Yeah. So it's not cheap, but it's also a month is not, a year. So
yeah, no, that's right. Yeah, I mean in Chime it's a couple of weeks usually. So.
Yeah.
Okay. Well, we're at the hour, and I am going to have to take off. But other people should feel free to stay on and ask more questions.
Thank you very much.